So we'll have Sabieh Anwar from Lahore University of Management Sciences in Lahore, Pakistan. And so, Dr. Anwar is a professor of physics and former dean at LUMS. LUMS is the acronym. So he's among the principal founders of the school's experimental facilities and curriculum. So ideas from his physics instructional laboratories called PhysLab have been replicated in about 10 Pakistani universities. He's played an important role in introducing innovative learning tools, mostly revolving around insightful but homegrown physics experiments. So nothing here has been bought by from a commercial supplier for a lot of money. It's really made in-house. And anyway, so he was the recipient of the TWAS medal and for physics for Pakistan and the National Innovation Prize in 2015. So anyway, so I've been following Sabieh. We just met, but I've been following his what he's been doing for many, many years, and it's really inventive. So he's first going to talk about easy to do single photon experiments for quantum education. So photons are pretty much the fundamental particle, a quantum particle, because they are a particle. And maybe they're also a wave. But at any rate, so that's going to be the first talk, a short talk, and then he's going to go into a demonstration. And I think the demonstration is showcasing the properties of light and where it comes from, a peep into the quantum world. So that will follow immediately, but that'll be, you see a lot of equipment being set up here, and again, it's not expensive. You can do this in Ghana. And so he's gonna demonstrate for you, but also give you a lecture on some of the important and interesting properties of photons. So, all right, Sabieh, are you ready? Whenever you're ready, go ahead and take off.
Thank you, Joe, for the invitation. I'd like to thank the organizers, particularly Richie, for inviting me. I come from Pakistan. I hope most of you know where Pakistan is. It's in South Asia, the 6th or 7th most populous country in the world. And today, I would like to talk a little bit about quantum education, but from an experimental perspective. So can you kindly bring up my slides, please? Okay. And can I have the slider, please? All right, so I'm going to talk about doing experiments with light. So this morning's sessions, including the previous one, were eye-openers really. They have really kind of illuminated the quantum world. They've shown to you what the counterintuitive notions of quantum physics are. They've shown to you what the qubit is, how do we process quantum information, and what promise does quantum information science and technology harbor for the human civilization. So what I'm going to do in the first 20-25 minutes of my kind of speech here is to give you an example of a laboratory that can be set up in Ghana. So there was a question about setting up laboratories. Now all of this is not just something that you read in a textbook or simulate or do mathematical calculations. In fact, it's easy to do quantum mechanical experiments, quantum optical experiments, experiments in quantum information right in a university laboratory. And it will not be very far from now when these laboratories will be established in colleges and pre-university institutions. So everything is becoming easier. As you know, technology is being democratized. There's a huge movement which is called the do-it-yourself movement, in which people build their own things. So the democratization of technology has kind of triggered interest in building experiments that evoke quantumness. So I'm just going to give you a few examples of that. And all of this is work that we've done in our in our laboratory, and this work was actually done by undergraduate students. So it didn't even require a PhD to kind of build these things. These were engineering students from an engineering university who got together. I was interested in the idea, and over a period of 2 or 3 years, we actually built a laboratory which highlighted purely quantum mechanical effects. So all of this is very accessible. We've also written a book, some advertisement for our book. Now this book is now in its second edition. It's published by the Institute of Physics, UK. And what this book does is that it gathers and collates all the theory that is needed to build these experiments. It introduces quantum states, unitary operators, the conundrum of measurement in quantum mechanics, and then it shows you how to implement these ideas with what we call photons. Now what are photons? So we have light everywhere. Light is everywhere. If you read the Genesis, the opening lines of the Genesis talk about light. So light is everywhere. But the light that we are accustomed to, for example, in this auditorium, it's not quantum light. It's classical light, and it has properties that are still not quantum. So if you kind of go into the realm where you come face to face or eye to eye with the tiny corpuscles, the tiny particles that this light is made up of, which are called photons for historical reasons, then you enter the quantum realm. Then you start kind of talking about quantum light. So if you go to that realm in which you are able to generate single photons and do manipulations with them, then you're truly doing a quantum mechanical experiment. So with normal light, even this laser that I have in my hand, or the lasers that I'm going to show you, they generate light through quantum mechanical principles, no doubt, but the light is not quantum, it's still classical. So if you somehow are able to break up or disintegrate your stream of light into those particles, you go to the scale of the particles, you get single photons. And that's what I call quantum light. So this book and this repository of experiments explains how to generate these single photons in the laboratory in a low-cost setting. It's not a shoestring budget. It's not ultra-low cost. It's not tens or hundreds of dollars, maybe thousands of dollars, but still very accessible. Okay? So you don't need a cryostat or liquid nitrogen or liquid helium, or you don't need to be very close to the zero, absolute zero. You still work at room temperatures, and by far, I think single photons, as well as NV centers, by the way, are the most accessible technology that can help in quantum education. And we have these laboratories in Pakistan. Several other developing countries are building such laboratories. So this is something that I would motivate Ghanaians and other Africans to commit to. So this is how simple this is. This is just an optical table with loads and loads of optical components, very similar to the table that I've set in front of you. And these are, I think, master level students trying to generate single photons and do different kinds of experiments. This is another view of this quantum laboratory. By the way, I have collected a collage of other photographs from our laboratory in Lahore. We do a lot of stuff with optics, magnetic resonance, and we also have lots and lots of school students, interns from around the country and occasionally from abroad come to our laboratory and spend their summers or vacation or get training for international competitions such as Olympiads in our laboratory. Now, this is what a quantum computer would actually look like. So this is just a small digression into what a quantum computer might look like. So this is one platform for quantum computers which is called a superconducting quantum interference device. If you break open the outer covering of that device, which looks like a big thermos flask, so there is a melange of wires, gold-coated wires that are bringing in microwave signals to a squid, to a superconducting chip that is placed at cryogenic temperatures, currents coming in, going out. Those squids act as the qubits, they process the information, they interact with one another, and you have a classical control mechanism that is controlling these qubits. So I will bypass all of this information. You've already had enough of history lesson. So there are different ways in which you can really look at the quantum world. So the quantum, it's hard to define what quantum really means, by the way. So there are different characteristics of the quantum world. There are different tenets of quantum mechanics. Different properties that become highlighted in the quantum world. You know, quantization, okay, everything is quantized, energies are quantized. You've had your interaction with the concept of superposition. Qubits can exist in quantum states that are superposition. You haven't heard a lot about entanglement. So entanglement is a property which, it's a kind of superposition, but a correlation between different qubits which cannot be explained classically. So if two objects are entangled, I perform an operation on my object, and a measurement on my entangled pair that is distant, far away, will be determined by the operations that I perform. And the physical distance between these two parties in the composite pair can be kilometers, it can be hundreds of kilometers, and they could even be light years away, thousands of light years away. So this is something, entanglement is an idea which leads to the power of quantum computers, okay? Of course there is interference because these quantum objects act like waves, and I'm going to give you a demonstration of this shortly. And then there's the concept of uncertainty. Now when we learn physics or science in our schools, we really want to think that science is exact. You have a meter rule, you measure something, you have a certain error bar. But if you have an electron microscope and you're measuring distances, the error bars get smaller because the resolution of your instrument gets smaller. But nature stops you somewhere. Quantum mechanics stops you somewhere. It stops you at what is called the Planck limit, at the uncertainty limit. You can't know something better than what the uncertainty principle allows you to know. So there are fundamental limits on how good a measurement you can make. There is always some uncertainty in your measurement. And if you want to know the position of something better, its speed diverges. You get more imprecise or ignorant about the speed. You try to capture one property, the other property kind of eludes you. Okay, so this is the uncertainty principle. And of course, this property of measurement. There was a question about measurement in the morning. You measure something, the quantum state changes. So quantum objects are really, really fragile, very fragile. That's why you want to keep them cold. We do live in a quantum world, but we don't see it because we live in a hot world. This world is at 37 degrees centigrade. It's a warm world for these quantum entities. But if you really want to see quantum properties manifest, you really need to go to the ultra-cold scale or to the ultra-small scale. So measuring something kind of disturbs, and the environment has a property to measure an object. So you want to keep your quantum systems away from the environment, in a secluded environment, so that they don't decohere or wither away, okay? So these are the basic tenets of quantum mechanics. So how does a single photon laboratory work? So you want to observe all of these phenomena in your laboratory, be you a school student, a college student, or a university student, or an engineering professor. Any of these properties can be studied with single photons. Now what's the basic idea of a single photon laboratory? So the basic idea is that you have a laser. Sorry, the pointer doesn't work. On the screen, you have a laser which is shown at the left by a purple line, and it falls onto a pair of crystals. Those crystals are cut in a special way, and they are nonlinear crystals, special material, a ceramic, barium titanate, and out come two beams that are shown in red in this view graph. Now those two beams, so one photon comes in and two photons go out. Now those two photons are single photons and they come out at the same time. Their polarizations are linked together, their directions are linked together, and they constitute what is called an entangled pair of photons. So a photon of a pump beam comes in and two entangled photons are produced. Now those photons act like your qubits. And you can do manipulations with them, you can measure them, you can transform them, you can do all kinds of experiments in quantum information and quantum computing, teleportation, quantum communication with this supply of photons. Now, conceptually, it's a very extremely simple design, right? Now, when these photons, these red photons come out in pairs, I have different kinds of optical elements, beam splitters, detectors, and all of these. Now these detectors are special and they are the only expensive thing in this experiment. Because these detectors have the property of being triggered by a single photon. These are single photon detectors. Now the human eye is very sensitive. If you look at the retina of the human eye, it is triggered by about 50 or 60 or 70 photons. There are certain animals that live deep inside the sea, in the darkest abysses of the sea, whose retina are triggered by a single photon. So these detectors are a marvel of engineering, and they are cooled by by Peltier coolers. And when a single photons hit them, they produce a signal, an electronic signal, a pulse. And those signals are then counted. Those signals are shaped, and all of those pulses are counted, and the data is transferred into a computer. So you count the number of pulses. And there's a question this morning about probabilities. Quantum mechanics gives you the probabilities of what you can see. That's the best quantum mechanics can do. So these probabilities correspond to the number of photon pulses that you receive. So you count the number of photon pulses. If the experiment is long enough, it's been running for long, those photon counts correspond to probabilities. Okay? So you do an experiment large number of times, the frequency of outcomes becomes the probabilities. So those photon counts are counted on a computer digitally, and those become your measurement outcomes. So you're able to measure. So in the previous talk, there were a listing of 4 criteria that you require for quantum processes. Generally, they are called the DiVincenzo criteria. You need to generate photons, generate qubits, you need to transform them, you need to measure them, you need to make your system scalable. So all of these properties exist inside these photonic implementations. So this is another schematic view of how the single photon laboratory looks like. A laser beam coming in, it is redirected by mirrors, and the BBO are the 2 crystals. Most of the laser light goes unimpeded, but that doesn't concern you, that you just dump it, you just forget it. But there are 2 beams that come out at an angle, all right? And those are your entangled photons. And you can manipulate them, and you can play with them, and you can measure them, and do all kinds of experiments. So this is how the thing looks like in actuality in a laboratory. And mind you, this is not very expensive, maybe $10,000, and still expensive by some standards, but on a relative scale, if you look at the quantum computing community, and out of these $10,000, perhaps it's about $6,000, $7,000 for the detectors. The rest is simple. And our book actually has the blueprint or the shopping list for all of these components. You can 3D print the mechanical parts yourself. You need to buy the crystals, a laser, and detectors, and that's it. So all of these are technical details. These are what the detectors look like. And this is what the pulse from a single photon looks like. So if you look at the time scale, it produces a pulse of the order of tens of nanoseconds, and you have a circuit, a fast circuit, that creates this undulating structure into a nice square-shaped pulse so that you can easily count it. Okay? So this is about a 10 to 15 nanosecond long electronic pulse that you're counting. All of this goes through wires into an FPGA. Now, electrical engineers will be very kind of triggered and catalyzed by the word FPGA. An FPGA is it's not like a microprocessor, but it does the same thing as a microprocessor, but you can reprogram it over and over again. So you learn a language, generally Verilog, and you program your FPGA board, which is very cheap, tens of dollars, $40, $50, $60. You program your FPGA so that it can count the pulses that are coming from the different detectors. Everything then goes into the computer, and then you can do marvels. So you can count how many pulses do I get on detector A, B, B prime, A prime. How many pulses do I get on A and B at the same time? These are called coincidences. All right? A, B prime, A prime, B, A prime, B prime, A, B, B prime, which are threefold coincidences. And the entire structure of quantum information is built around these pulse counts, the counts of the singles and the counts of the coincidences. Now, all of these are technical details. You can also image these photons. You can have a camera or a telescopic arrangement that can show you these single photons, entangled photons. And all the rest is slightly technical, so I will just bypass this. But the key idea is that if I go back to my experiment here, just focus on the bottom part. What is a photon? This helps me define a single photon. And that's probably the only thing that I'm going to talk about. What is a photon? Now, a photon, naively, is a particle of light. But what is a particle? Now, when you talk about quantum information, quantum mechanics, semantics and your language play a very important role. So, it's very hard to define a photon. Generally, when we say the word photon, the concept that comes up in our mind is a photon is an object that cannot be detected twice. A photon can only be detected once. What does that mean? This means that if I have a photon coming in from the left and it falls onto this beam splitter, BS, which has two output ports, one port corresponds to the photon being transmitted, and the other port, which is pointing in the downward direction, corresponds to the photon being reflected. So it's like a half-silvered mirror. It lets a photon go through with the probability 50% and transmits the photon with the probability of 50%. And you put detectors on the two output arms, only one of the detector is going to click at a time. That's what a photon means. Which means that you can never obtain coincidences between B and B prime. There is absolutely no chance of a coincidence. And that's what a photon is. So you measure these coincidences, and if the coincidences go to 0, then you have achieved single photons. This is your signature test for single photons. So when we perform this experiment, for example, at tau equals 0, this curve just droops to 0. It falls down to 0, which means that we've created single photons. You get exactly the same behavior as seen on the top right curve for coincidence measurements, which correspond to delays of about 0 seconds, 0 nanoseconds. The coincidences drop to 0, which means that you've created single entities, single quantum entities, okay, single photons. And then you can do all kinds of state measurement. You could, one really cool experiment which captures all of quantum mechanics is the wave-particle duality experiment. And can the students who already know about wave-particle duality raise their hands? Probably you study this in high school. Engineering students. Which class are you in? Can you just speak up, anyone? Class 9, 8, 10, high school? Don't be shy. Come on. Which class are you in? Which grade? You high schoolers? Just speak up. Don't be shy. This is a part of our collective training. Okay. So sometimes an object acts like a wave, and sometimes it acts like a particle. Now, what is a wave? Suppose I'm on the sea, I'm in a boat, and if certain undulations, certain vibrations of the water come, and I kind of toss around like this. See? This would mean I'm being struck by a wave. A wave is a continuous stream of disturbance, and it spreads out. A wave, the water wave is spread out, isn't it? So it's delocalized. But if I'm on the sea and I'm kind of static, and all of a sudden I go like this, that's it. I'm struck by a particle. A particle happens at a precise location in time and space. It's localized. So light sometimes behaves like a wave, and sometimes it acts like a particle. The property of wave, can you move back to the, okay, so the property of a particle is that it doesn't interfere, and the property of a wave is that it interferes. So you can get regions where photons can go, and regions where photons can never go. So this, depending upon how you observe, the wave and the particle properties coexist. Now if you try to find out, be extra clever and try to poke into this experiment and determine whether the object is a wave or a particle, then it kind of disturbs the object, and you do not see this wave-particle duality. So this is the central kind of idea of quantumness. And then you have these beam splitters, and also you have quantum erasure. So all of these experiments are done with single photons, but these are all, I'm just going to scan through the slides. These are fringes that you get with single photons. And you have non-locality, you have entanglement. But the key idea is, I'll try to take a break here and move to the demonstration straight away. But the key idea that I wanted to show is that it's possible to do quantum mechanical, truly quantum mechanical experiments in the laboratory. See interference, see wave-particle duality, see entanglement, non-locality, and things of that sort. So at this point, I would like to see if there are any questions before I move on to the demonstrations.
As Sabi, I'm going to get the answer for your previous question. So let me go back and sample. I'll just pick anybody that's, so which grade are you in? Are you in high school? What's your name? I'm Joe.
Carlota.
Okay, very nice. So what grade?
Form 2. SHS 2.
Fourth year senior high school.
Second year.
Second year high school. Okay. Okay, you.
Second year high school.
Second year high school. Everybody say.
Second year.
Second year high school. Second year high school.
Yes, please. Yes, please.
You guys are all shy. Boy, really shy. Okay. See, if I'm going to come up and make a fool of myself, am I making a, yeah, okay, never mind. Okay, good. So you're all second year high school. Okay, everybody's second year high school. That's the answer. Okay, questions?
All right, any questions about single photons and the kind of experiments you could do with single photons? Sorry, I had a lot more slides, but I just want to keep it very, very general here and move on to the demonstration. Yes, please. You always ask very good questions. Here you go.
Thank you very much. So please,
Currently, it's known that when it comes to quantum photonics, it is very hard to capture just one photon. Yeah, so I'm actually very curious in how this setup is going to work, because I think the best we have so far is to emit some amount of laser, but trying to reduce it so much that we get near zero, then that means it's single. But is there any advancement, I think, in your experiments that will kind of take it from there, maybe do something a bit different to that?
Can you move to the presentation, please? Very good question. So, why are these single photons? Okay. Now one would imagine that if I have a beam of light and I attenuate it, attenuation means you kind of block it, and you get to the level that only one photon comes out at a time, you get single photons. But that's not how single photons are generated. Those photons that come out may be coming out one by one, but still they do not qualify as single photons. That's not quantum light. That's attenuated or highly attenuated or extremely faint or feeble light, but still classical. So what distinguishes quantum light from other sources of light are statistics. So look at this curve. So now if I have a laser, if you have a very coherent, nice, continuous, pure laser, if you chop up the beam of light into small sections, look at the top left, you have red dots in some sections. Those red dots correspond to photons. So we've chopped up the light into minuscule intervals, and each minuscule interval has a photon in it. This is spectrally pure light, hypothetically monochromatic, which is impossible to get. But look at the ordering of the photons. The photons are still irregular. So this is dim light, strongly attenuated light, but still coherent or classical. Now, on the contrary, if you look at the top right figure, I've chopped up the light, and if it's quantum light or single photon light, there is a periodic disposition of photons. A photon, an interval with a photon followed by two lapses, one photon, two gaps, one photon, two gaps. So it's a highly anti-bunched stream of photons. They don't coalesce, it's a periodic arrangement. So the difference between single photon and other kinds of light lies in the statistics. So single photon light is sub-Poissonian, as it is called. So how do we achieve this in our experiment? In our experiment, really, when light comes in, those BBO crystals create two single photons. But this is a highly inefficient process. So if, say, 100 billion photons are coming in from a 1 milliwatt laser, only one out of those 100 billion incoming photons will produce an entangled pair. It's a highly inefficient process. And we're using this inefficiency to our advantage. Because now we have a regular stream of photons coming out at a manageable rate, which does not saturate our detectors, and those are truly single photons. And then we do a scheme which is called heralding. Heralding means that if A clicks, if detector A clicks, we know that B would click at the same time, because those photons are always coming out in pairs. So A heralds the creation of a single photon on the detector A. So we only look at those counts at B when there is a coincident detection at A, when there is a heralding at A. So it's like an artificial way of creating single photons. True single photon sources, which are deterministic, are very hard to build in the laboratory. But even though commercial systems are available, but they're very expensive. Okay, so I hope I've answered your question, but a very good question. May I ask you, are you an engineering student or a professor? Very nice. Any more questions about this part? So with these single photon experiments, you could do entanglement, you could do non-locality, you can do tomography, you can do interferometry, quantum erasure, delayed choice, all kinds of experiments. So probably you'll have to look at our book or at our website for that.